Welcome back to another episode of Dave Does Math from Home. We are still talking about partial derivatives. Now we're doing part two. Part two of our partial derivative lesson is going to be mostly focused on second derivatives. We're going to see what kind of weird shenanigans happen when we take the derivative of something and then we take the derivative of it again. Only this time there's going to be a couple different flavors of second derivative. We already know that in this three-dimensional setting where x and y are independent and z is dependent, because we have two independent variables, there's two different derivatives. There's the derivative, the partial with respect to x and the partial with respect to y. So when we start doing second derivatives, we're going to get even more options. So let's just dive right in and see what that looks like. Before I can get some second derivatives, I need to get some partial derivatives, first derivatives. So dz dx should be derivative of x squared is 2x, y squared hangs out like it was just a coefficient. We've already talked about this derivative of xy business, so that's going to be e to the xy times y. And the partial of z with respect to x, or sorry, y this time. I just did x. So the partial with respect to y should be 2x squared y minus e to the xy times x this time. So I have these are my first derivatives, my partial first derivatives, derivative with respect to x, derivative with respect to y. Based on this, I'm going to start with this partial with respect to x. I'm going to do another dx to this. I'm going to take a second derivative of this with respect to x the second time. So we saw a little bit of this Leibniz's notation for second derivatives. We saw a little bit of this at the end of Calc 2 when we were doing parametric functions and polar functions and derivative of those. The way we write this second derivative is the second derivative of z with respect to x twice. So this exponent here goes on the d. That's how we know it's a second derivative. This means it's with respect to x both times. So that is going to be derivative of this with respect to x should just be 2y squared minus y is just going to hang out like it's a coefficient. The derivative of e to the xy should be e to the xy times y. So after I simplify this, I should get y squared e to the xy. One of the y's was already here. It's just hanging out like it's a coefficient because it's not really involved. The other y gets introduced from the chain rule, just like this y got introduced from this chain rule. So one of them started there, the other one gets introduced by the chain rule. Gives us two y's. So we have 2y squared minus y squared e to the xy. This is the second partial derivative with respect to x twice. I'm going to take a second partial derivative here with respect to y a second time. And that will give me second derivative with respect to y twice should be derivative of y is just 1. So 2x squared minus, I have 1x here. I'm going to get a second x from the chain rule when I do the derivative of e to the xy. And other than that, the derivative of e to the xy doesn't really change. Derivative of e to the xy is e to the xy times x, because that's the derivative of the inside. And that x combines with this x that was already here, and we have two x's. Here's a sort of symmetry here. That's two of the partial derivatives. This is what happens when we take derivatives with respect to x twice and with respect to y twice. So now the question becomes, What happens if we start mixing these partials together? What happens if you take the derivative with respect to x and then you take the derivative with respect to y? Let's find out. I'm glad you asked. If we take the derivative with respect to x and then with respect to y, we're going to call that delta, second derivative of z with respect to x, I can't draw, and y. And we need to take this derivative with respect to y. So that should give me 4xy. The derivative of y squared is 2y. So that'll combine with this to the 2, and then the x and the y will stay. So 4xy minus, here's a problem. When we do the derivative of this with respect to y, we need to use the product rule. This is two things that are multiplied together that both have y's in them. Here, this is not a product rule problem because every time we take the derivative of this thing, only one piece of it has the variable we care about, and we're pretending the rest is constant, which lets us pretend it's a coefficient and we don't have to use the product rule for coefficients. Coefficients are safe. This, we can't pretend like these things are coefficients anymore. When we do the derivative of this with respect to y, this is e to the xy is a function of y is a function of y. We have to use the product rule here. So, I'm going to leave the minus on the outside and we're going to do product rule stuff. Product rule says it's going to be the first, e to the xy, times the derivative of the second, which is 1, plus the second, which is y, times the derivative of the first, which is derivative of e to the xy is e to the xy times the derivative of what's on the inside. The derivative of the inside with respect to y is just x. So we get 4xy minus e to the xy plus xy e to the xy. You can all see what this looks like. I'm going to simplify it a little bit with the eraser because I'm running out of space. I'm just going to put this x in front. So this is x, I'm writing on top of a big blemish on my whiteboard, x, y, e to the x, y. So that's what happens when we do the derivative with respect to x and then with respect to y. Hopefully I've left enough space here for you to anticipate what's happening next. I want to see what happens if we take the derivative with respect to y and then with respect to x. If we do this, we will get the second derivative of z with respect to y, then x. And that will equal, we're taking the derivative of this now with respect to x. The derivative here should be 4xy. Derivative of x squared is, derivative of 2x squared is 4x. Y hangs out. Minus, this is going to be a product rule problem again. So, first, e to the xy times the derivative of the second is 1, plus the second is x. The derivative of e to the xy with respect to x, we've already done that. The derivative of e to the xy with respect to x is e to the xy times y. So that's the derivative of this with respect to x. So I'm just going to put the y in front. And there it is. X times y e to the xy. Here's the really good news. You might not be ready for the good news right now. You might still be reeling at what all of this happens, because this is 6 derivatives that all involve the chain rule and the product rule. This is officially a weird looking mess. But thank you for staying with me for this long. If you need a break, pause the video, take your break. If you don't want a break and you want to go directly into the good news, here's the good news. These are the same. It doesn't matter if you take a derivative with respect to x and then y, or if you take a derivative with respect to y and then x. Those things should be exactly the same. This is called the mixed partial. And it's usually called the mixed partial. It's not a mixed partial. It's not like one of many possible mixed partials. It is the single unique mixed partial. There's only one because the order in which you do this doesn't matter. And if you take a derivative with respect to x and with respect to y, you should get the same thing either way, no matter what. That's usually, it can be a good way to check your answers to see if you've done these derivatives right. If you think you may have made a mistake on this, take another derivative with respect to x, take the derivative here with respect to y, see if you get the same thing. Can be helpful. I guess on a problem that's this complex, it's probably not helpful. But on most problems, which will be less complex than this, you can check your partial derivatives by finding the mixed partial and making sure that it matches. Because it should always match. And that's the nice thing about that. So I set this up to try and sort of trick you into thinking that there were 4 different second derivatives. There are not. There's just the 3. There's x twice, there's y twice, and there's the mixed one in the middle. So you have 2 first derivatives, you have 3 second derivatives. We kind of don't ever really deal with third derivatives in Calc 2. I'm sure there are some practical applications that could use that. They just aren't things that we really need to cover in this class. If you do decide that you need to cover them somewhere, then I'm sure that they will help you out with that transition. So that's the mystery of the mixed partials solved. I'm going to erase this. We're at 12 minutes. So I'm going to erase this and we'll do another couple examples of second derivatives that hopefully involve less chain rules and product rules. Hopefully we'll get some nicer looking stuff. Let's do z equals, let's just do an entire polynomial. Everything third degree. We'll do 1x cubed minus 3x squared y minus 3xy squared plus y cubed. I guess I don't need the 1 there. All things third degree. I should note that this counts as a third degree term because the total degree here is 3. When you got multiple variables in the same term, then you add together their powers to get the degree of that term. So all of these are third degree terms. This is a third degree polynomial. Let's find its derivatives. Partial with respect to x should be 3x squared minus 6xy minus 3y squared plus nothing. That term is gone. The partial with respect to y should be nothing. Minus 3x squared minus 6xy plus 3y squared. The second derivative with respect to x twice should be 6x minus 6y plus nothing. The second derivative with respect to y, I hate drawing these squirrely d's. Second derivative with respect to y twice should be nothing, nothing, negative 6x plus 6y. And the mixed partial, second derivative of z with respect to x and y, should be, you can get this in either of two ways. You can start here and do a derivative with respect to y, or you can start here and do a derivative with respect to x. I'm going to do them both to make sure I've been doing this right. I'm going to start here, do the derivative of this with respect to y. It'll give me nothing, negative 6x minus 6y. Now I'm going to start here and verify that by taking derivative of this with respect to x. This will give me minus 6x minus 6y and nothing. So, negative 6x, negative 6y is the mixed partial either way. They agree. That's what we wanted. There's a nice, pretty straightforward polynomial to introduce some of these ideas. I'm going to see if I can, or should I do a weird one? Let me see if I can get some more weird stuff with chain rules and product rules so that we can remember what all that looks like. Let's do one more example. Z equals, let's do x times the sine squared of x y squared plus 3. So I want the derivative with respect to x. Right away that's going to be a product rule thing, because I have x times the sine of something. So we'll do the first, the derivative of the second. Derivative of the second is a weird looking chain rule thing. So the outside here, remember that sine squared means sine squared. So the outside here should be 2 of these things to the 1. And this thing is the sine of x y squared. And then I have to multiply that by the derivative of the inside. The inside is the sine of something. So the derivative of that should be the cosine of x y squared. And then I have to multiply that by the derivative of the inside of this, which is just y squared. So that's a weird looking mess, and I don't want to do a second derivative of that, so I won't. But I will do, oh no, this is just the first half of the product rule. Plus, so this is the first, this whole thing is the derivative of the second. So I need to do the second, sine squared x y squared times the derivative of the first, which is 1. Okay. This was probably a mistake, but I'm going to finish the first partials at least. Let's do the partial derivative of this with respect to y. This I think is going to be much easier because now this isn't a product rule problem anymore. Now x is just a coefficient, it's safe, I can leave it alone, it's fine. I still do have to take the derivative of sine squared xy squared, and that's going to look a lot like this. Derivative of something squared is 2 of those things to the first. Derivative of sine of something is cosine of that thing. Derivative of the inside of this now should be 2xy. And then I'm done. No product rule. hopefully that was helpful. A little helpful review of product rule, chain rule stuff. I'm at 20 minutes, so I'm going to end this. Good luck.